In this section, we start a new chapter, namely linear algebraic equations. Let's start with a very simple case with one single equation for one single unknown. And then later we will generalize this to cases when there are more equations for more than one unknowns. So let's consider something very simple. Say 5x is equal to 3. Well, no problem. We divide by 5 and we have the solution x is 3/5. Well, no problem. If instead of 3 we have 0 on the right, then we call such an equation homogeneous. And homogeneous equation has always 0 solution, and as it will turn out, in some cases we can have even non-zero solution for larger systems. Now, what if instead of 5 we have 0? Obviously, 0 times any real number is 0, and that is never 3. So this has no solution. Sometimes we write it x is an element of empty set. Yes, it may happen that a linear equation has no solution. And also, we can have a case 0x is 0. But this time we have 0 on the left, 0 on the right, and this is true for any real x. So we have infinitely many solutions, and x may be any real number. So we can have one solution, no solution, or infinitely many solutions. Well, there are equations that have, say, 2 solutions. An example being quadratic equation, but this is no more linear. By a linear equation, we mean an equation where the unknown objects, x or other variables, are in a very simple operation. Multiplication by a number and addition. No more operation allowed. Okay, so that was for one equation for one unknown. And let's consider a larger system. We can have an equation like 5x minus 7y is 1, and 2x plus 3y is 2. Then it is convenient to introduce the matrix of the coefficients 5, minus 7, 2, 3. It is convenient to introduce a vector b arrow with the right hand side. And it is convenient to introduce the vector of unknowns x arrow, which has as components the 2 unknowns, x without arrow and y without arrow. And then, if you remember the multiplication of matrix and vector, we can write this equation into a very simple compact form. X times a times the vector of unknowns is the vector of right hand side. Because if we rewrite a in this form, using the numbers 5, minus 7, 2, 3, and x arrow is the column vector with the unknowns, x and y, then you remember how to multiply. We consider a row in the first matrix times this column, so this is 5x minus 7y. And then 2x plus 3y. And this is exactly what is on the left. So ax is an abbreviation for all this wrong writing. Well, and b arrow is just a vector with the numbers on the right hand side. Well, to be very careful, very precise, we should make absolutely clear that this and this means equality between two numbers, but this equal sign is something different. This relates to vectors. So actually, we should write a different graphical symbol. Unfortunately, in mathematics, it happens now and then that we use the same graphical symbol even for different meanings. So this is equality between two vectors, and this is just between two numbers. Yeah, we should call this into brackets as well. So now for some time we will discuss the system of linear algebraic equations in the form Ax is equal to B, where A is a given fixed matrix, X is the vector of unknowns, and B is the right hand side, the vector of numbers. If the matrix is m times n, then we have n unknowns and we have m equations. So this is the number of unknowns and this is the number of equations. In the very first case, n was 1, n was 1. Here, m and n was 2. They may be large positive integers, and they may be even different. You can have the different number of equations and different number of unknowns. Let us start with homogeneous equation. Namely, Ax is 0. Such a homogeneous equation has always one solution, namely 0, also called trivial solution. But sometimes it may have also non-trivial solution. Consider an example. X plus y is 2. If homogeneous x plus y is 0, 2x plus 2y is 0. Well, we see that they are not independent. The second equation is just 2 times the first one. If we write the matrix 1, 1, 2, 2, and for the manipulation, it is convenient to introduce another matrix, namely augmented matrix, denoted A bar B. We just add the right-hand side column to the matrix A. Well, a very convenient and stable method is to solve such a problem using the Gaussian elimination to bring the matrix to the upper triangular corner. Then we copy the first row, and to get to 0 here, we take the second row and we subtract 2 times the first one. But then we get 0, and the 0 line corresponds to an equation 0 is equal to 0, and we can cancel this equation. So we have 1, 1, 0. This corresponds to the equation x plus y is 0, that was the first one. Well, you know that this has the solution y is equal to minus x, where x is any real number. Sometimes we choose another letter, say t, for parameter, and we can write x is equal to t, y is equal to minus t, and t is a real parameter. Practically speaking, y is minus x corresponds to a line like that. So you see we have infinitely many points, infinitely many solutions satisfying this system of equations. If we have this homogeneous equation, then this looks simple, but it is an important case. Actually, the set of all the solutions to such a homogeneous system is quite an important object, so important that it has its name. This is called the null space, or a kernel of the matrix. Kernel, or null space, of a matrix, denoted by n, is just a set of all the vectors x such that ax is equal to 0. So for this matrix, 1, 1, 2, 2, the kernel is the set of all vectors x, y from R2 such that y is minus x and x is any real number. So this is the kernel, or equivalent to null space, of a matrix, the set of all the solutions to the homogeneous equation. And this set has one important property. If x is in the null space, then any multiple of this vector is in the null space as well. Because if ax is 0, then if you multiply the vector x with any scalar, with any number, then it still satisfies this equation. And also, if x and y are in the null space, so is their sum. Because if you consider the sum of x and y, now with arrow, that means two vectors, and you multiply by the matrix, then this is a times x plus a times y. But if x is in the null space of A, then ax is 0. And similarly, if y is in the null space, then ay is 0. But 0 plus 0 is 0, so you see a times this new vector is again 0. So the sum of the two solutions is again a perfect solution to the homogeneous system. Well, and because we can multiply x and y by any number, then we can combine these two results, that if you have two solutions to the homogeneous system, then any linear combination of them is again a solution to the system. And this is true not just for two. If you have any number of solutions, then any linear combination of them is again a solution to the homogeneous system.